And I will say that the importance of optimism and confidence and just can't be overstated. If you go in with a mentality that I can really look at any problem, no matter how hard it is, and give it a serious try. So example is, suppose you're working on a problem and then someone comes up to you and says, oh, you know, that problem, if you solved it, you'd be able to solve this unknown conjecture that's been open for 30 years. And then how many would say, oh, okay, then I'll put it aside, I won't get it. Don't do that. If you hear that, then you say, oh my gosh, that's great. And then go and explore it as much as you can, understand everything you can about it. Because maybe you will get that problem that's been open for 30 years. So anyway, and then just, you know, form support groups and networks so that you can kind of feel in your zone and in a place where your confidence, self-confidence can grow. Okay. Today, this is an example of challenging my self-confidence because I'm talking about a subject which I really had to learn purposely for this talk series, PKI on the internet. So PKI was discovered about 40 years ago, and I kind of am an expert of understanding in an abstract sense, but I said, well, let's see how they actually do it on the internet. I know they do it, but where? Where are the bits? Where are the internet packets? So that's the goal of this lecture, is to get a little grungy and go into where is all that stuff on the internet? Okay. So we're going to give, I like to start with a brief history, because for me, it just puts everything in perspective for me. And then what we handed out are some live examples of internet output from a program called Wireshark, which I think you've been introduced to. It captures internet packets and it kind of parses them for you. And then I'll talk about TLS, which is the the security that HTTPS is based on, and Cipher Suites, which are where you choose a set of public key algorithms together with supporting algorithms for encryption, hashes, and et cetera. And then finally, internet protocols, which are like envelopes within envelopes. ARPANET in the 1960s was developed as a research tool for universities and military or government laboratories, and you could say that was the first internet. 1987, NSFNet connected 6 large mainframes over phone lines. Remember those phone lines, anybody? My poor kids, we made them use phone lines because we didn't want them to get addicted to the internet. And finally, when they got to college, they got the I feel bad for them, I'm sorry. Sorry, children. Okay, so HTTP is a hypertext transfer protocol invented in 1989. And by 1996, browsers using HTTP were widely available. HTTP does not have encryption on it. With encryption, it's HTTPS, right? Okay. How about internet security? So mid-1980s, there was the Athena project at MIT, which was a non-PKI system of internet security called Kerberos, and it's still in existence today. When you're in a relatively small closed network, you can afford to distribute the keys to every pair of routers. So it's still a good system. On a smaller scale anyway. 1992, we had Pretty Good Privacy, PGP, by Philip Zimmermann. And then SSL was developed in 1994 by Netscape. And it evolved, or it was superseded by TLS, which is Transport Layer Security. TLS is the basis for security on browsers and security for file transfer and many other things. this became an internet standard in 1999, and it was updated in 2008 and 2011. Then finally, not in this lecture, but IPsec should be mentioned. It provides security directly between routers, where routers just have a shared key between them, and they simply encrypt to the next router with a shared key, decrypt that, and encrypt with the next key for the next router, and so on. So it gives additional security, and it is a basis for VPNs, but it won't appear anymore in this talk. So Wireshark is this package you've downloaded and you've been introduced to, and your handouts have the output from Wireshark. So it shows the IP packets that enter or leave your computer. And in the top part of the output, it kind of parses for you what it's doing, and the bottom part has the raw bits. So Emily and I sat in a cafe, and we brought up Wireshark, and then we went to Amazon, which apparently everybody is using Amazon as their example, because that was Kristen's example too. So then you filter on SSL, and that brings up all the packets that deal with public key infrastructure. So these are the two of the slide shots, and you have pictures of them, and I found out when I was practicing this talk that I kept having to flip back and forth, so it's easier if you just hold them. If you don't have one, I think Emily has them. So if you don't have one, raise your hand. Okay. All right. So let's take a look at what this has on it. At the top, it lists numbers 36, 37, the time. There's a source IP. That would be the computer address of the sender. The destination IP, the computer address of the recipient. The protocol being used. The length in bytes. And then some information about the packet. So this is all stuff that they very kindly decided to tell you the meaning of what's in the packet. Then you can click on something and you can scroll. So when I click here on this particular line, it will bring me to the window showing what that line indicates. So these are the actual raw bits at the bottom. At the bottom are the raw bits corresponding to the particular line which has been highlighted. Okay? All right, so we are, notice that every line contains a particular IP address 192.168.1.162. That is our laptop. I don't remember if this came from mine or from Emily's, but that is the laptop. The other addresses shown here are other, like Amazon server or whatever other servers we happen to have up, whatever other connections we had up. And it looks like there are two of them. So we're seeing a client hello twice. That's because there are two different IP addresses that we're simultaneously communicating with. And then, so we highlighted this particular one, and we highlighted this particular, we just looked for something that looked crippy, right? Okay, that looks pretty crippy, let's highlight it. And, and then, what is this thing? It's a Cipher Suite. It tells me I'm going to use elliptic curve, Diffie-Hellman, ephemeral key exchange. My signature algorithm will be elliptic curve, digital signature algorithm. And then, like, what is this Cha-Cha 20? Oh, that's Daniel Bernstein apparently made an encryption and method authentication scheme with a jazzy name. And so that's what that part is. And then the SHA-256 we recognize as a hash. So it's telling you all the stuff. And this Cipher Suite is completely spelled out in standards. So all this stuff can be found in standards. IETF is the group that's doing the TLS standards. And every single Cipher Suite, you can find an RFC, request for comment, which tells you exactly what the steps are and how how everything should be presented so that the computer will do the right thing, okay? All right, now you notice each Cipher Suite has a 4-byte code associated. So this one is CCA9, and there it is, CCA9. What we're doing here in the client hello is we're listing all the different Cipher Suites that we like, from favorite to least favorite. And so here we see CCA9. The next one listed is CCA8. And then the next one is CO13, CO14, 009C. And then they list more and more of them, and just a bunch of them. Yes?
What's the poly 1305?
That goes inside of this Cipher Suite, and that is a method for message authentication. Yeah.
What is a Cipher Suite in general?
So a Cipher Suite is a particular package of public key techniques combined with what kind of encipherment you'll use. Are you going to use AES? Look at some of them. So like, I think in the next slide I'm going to parse this down entirely and tell you what it is. But it tells you, because not all things go together well. So you can't just independently select, oh, I'm going to use this for encryption, this for, some things require other things to be paired with. So they make the suite all in one package so it can be coordinated as a single package. Yeah.
So the source and the destination seem to flip back and forth. So is that it talking back and forth?
Yes, each one of these is a different, each line here is a different packet, and so with a source and a destination. So it is talking back and forth. So if we look at just this conversation, client, hello, server, hello. Then comes certificate. Here's my public key certificate. Remember Alice and Bob? Change certificates. Okay, server key exchange. Let's do Diffie-Hellman key exchange. Here's mine. Okay, client key exchange. Oh yeah, here's mine. Okay, so it's going back and forth. Yeah.
So all these are happening within some Cipher Suite?
Yeah, the client hello has a purpose of listing the Cipher Suites I like. The server hello has a purpose of choosing one of them.
Okay.
Once they've chosen them, then they can, so the server hello, and then once they've chosen them, it's time for certificate, time for key exchange, time for all that stuff. And then at some point, application data is where you're actually starting to encrypt your stuff. So that's when you see Cipher going.
So where do these Cipher Suites kind of live? Like where is that information stored?
That's in the RFCs. The exact protocol composition of it is in the request for comments. And so you do have, in the process, each side will make up random numbers at times in order to create their Diffie-Hellman, and they'll send whatever information the protocol says in the exact format that the protocol says. So the point of the protocol is we know in principle what we're doing. If we were on the phone, you'd say, okay, here's my public key. Ready? Okay, ready. Okay, it's N, and here are the digits. Okay, are you going left to right or right to left? Are you hexadecimal? You have to specify all these millions and millions of little things, and that's what these protocols do. They're very, very detail-oriented, and it just tells you exactly how to do it step by step. Yeah?
I see a round trip here before starting the encryption between client and server. Is there any way to do it only with one round? Makes sense?
With one round to...
Just like start sending the payload as encrypted before like making a round
Well, you
between
first,
client and server.
if you did that, you would confuse the recipient because they don't know what method you're using yet. So if you start trying to communicate with Bob and just send a whole bunch of bits, he doesn't know, is this N? Is this P? How long is N? Or how long is it? So there are many, many.
Handshake before.
Yeah, the handshake is to sort of get yourself on the same page so that you can start doing the protocols. Okay? Any other questions? These are great questions. Yeah?
So these are like just packets that are incoming and outgoing from
from your computer where your Wireshark is set up.
Okay, because I opened it at the hotel and it seemed like there were lots of different IP addresses.
Oh, really?
It's the whole Wi-Fi network that you're on. You see
Okay.
Oh, you see everything. Okay.
Okay, because there was definitely a lot.
Oh, all right. All right, then I'm glad you've already played with it. And I have already given the disclaimer that I'm not an expert on this, so
Okay.
now you're calling me out. All right, anything else? Yeah.
Okay. Is it, so you said that they list a bunch of things and then you choose? Is that what you said? That like, they said
Yeah,
specific
so
that
in the client hello, they're listing, client is your browser. And the server is, some company usually, and so the browser goes first and says these are the protocols that I can support, that my browser can support. It depends if you have Mozilla or if you have Firefox or Internet Explorer, what preferences they have for their preferences, and then the server will just pick one of them.
Does it ever happen that your stuff is too outdated and the server's like, no, I don't want to talk to you?
Yeah, in the later versions of TLS, they will reject. I mean, actually, if you want more security, you should not make your list too long. Don't keep going down to the point where it's insecure. You don't want anything insecure on your list.
I see. Interesting.
Right? Okay. All right. Anything else? All right. So here's another sample output, and here, what do we do here? Emily and I, we just clicked on something that looked good. Okay, I think that looks good. Certificate, server key exchange, server hello. Yeah, let's do that. All right, so then what this is showing in the middle of the screen, it is showing stuff about the server key exchange. So it's telling us how long it is, the handshake protocol. We're using elliptic curve Diffie-Hellman. And what are the server parameters? What are the parameters? There's a named curve, which is labeled OX03. You could find out its equation if you want by looking in RFC. Okay? In fact, the name of this curve is SecP256R1. And it's got its own 4-digit hex code, right? And then public key length, 65 bytes. That's 520 bits. Why would it be 520 bits if the curve seems to be 256 bits from the name of it? Why do I need 520 bits for the public key if the curve is only over a 256-bit curve field? Any ideas? We've got a 256-bit curve, yet my public key takes twice that much. Yeah.
You have an XY coordinate?
Yes, you have an x coordinate and a y coordinate. That's why it doubles in length. And then it says what your public key is, and it says the signature algorithm, and that's RSA with SHA-512. Okay, that's good. And the signature length, 256 bytes is 2048 bits. Okay, so it kind of makes sense. Signature, that would be, all right, so for signing, they're using RSA, but they're also using elliptic curve DSA for key exchange. Then these are the actual bits of the exchange. I was hoping to find some of these bit strings down here, but did not. What appears to have happened is that they are still finishing up sending the certificate. So we're still seeing something from a previous package. All right. So here's a first thing that happens, TLS Handshake, and we saw that in the first Wireshark slide. We had a client hello, server hello, certificate, server key exchange, server hello done, client key exchange, change cipher spec, client hello done, application data. All this, numbers 1 through 4 is part of a TLS handshake, 1 through 4. item 5 is where you actually send the encrypted stuff. Okay. So during the handshake, the client, my browser, and the server, Amazon, use public key cryptography to obtain a shared key that'll be used to encrypt our session. It'll be used to encrypt all the remainder of the packet. No, not just the remainder of the packet, but the whole series of packets that are exchanged. Now we have a situation of one-sided authentication. Do you have a public key? I don't. But Amazon does. So this is a one-sided authentication. Amazon is okay with that because I have a password, I have a credit card, and they get paid, so it's okay. They don't want to just only accept customers who have public key certificates. That would really limit their business. Okay, so it's just the way things evolved. TLS does support two-sided authentication as well, but a typical transaction we would do is only got one-sided. And then the client and server hello have the main purpose to just agree what Cipher Suite we're using. So here's a Cipher Suite example. TLS, meaning it's part of the TLS package. ECDHE, elliptic curve Diffie-Hellman with ephemeral key. Sam? Oh, do I just hit cancel?
Yeah.
Oh, I could do that. I'm a technical person. Okay. So there we go. Right. Ephemeral means a temporary random. So I just make up my little A for the day, just myself, and he makes up his little B, and just for today. It's not part of your public or private key. And then ECDSA is elliptic curve digital signature algorithm. The description of that is on your protocol information that I gave out last time. It's also on one of the last slides. It's I think it's the same as almost the same or exactly the same as elliptic curve El-Gamal. So you'll find it. AES 128, that's advanced encryption standard with a 128-bit key, and it encrypts 128-bit blocks, and it should provide 128 bits of security. GCM means Galois counter mode, and it encrypts the jth block of the message by XORing it bitwise with the encryption under your key of the number J, and it's used because it's very parallelizable and fast. There are other types of modes. You can use AES in CBC mode, which is cipher block chaining mode. So there are choices for modes, and that is specified in here. SHA-256 hash function with a 256-bit output for use with key exchange and signature. I'll explain a little later that SHA-256 should have 128 bits of security, so that matches the security level here of AES. Yeah?
So, okay. I noticed here you say there's ephemeral. Is that fairly standard that when you want to connect to a server, you can have one side be the ephemeral?
In this case, both sides are ephemeral for this key exchange. However, Amazon is going to sign theirs, so that the ephemeral does not prevent man in the middle. So you do have to have authentication on top of that.
I was just wondering because of the post-quantum, maybe. The static option is not that great. So.
Okay. So the client hello, I think I've said it gives my browser's favorite Cipher Suite. Server hello, they pick one. Certificate, the Amazon will send its public key certificate. Server key exchange, that's half of the Williamson Diffie-Hellman key exchange. client is the other half of the client key exchange, is the other half of that exchange. Change cipher spec. That means I'm ready, let's start encrypting. And that's as soon as you've got all the information you need to figure out that we have an authenticated connection and to figure out what our shared key is. That's when you say, I'm ready, okay. Next, because you gotta say I'm ready, otherwise they won't know that your bits are gonna be encrypted. You gotta warn them. So, and then application data is just the actual encrypted stuff, and that should look like gibberish if the encryption is working right. So the Wireshark screenshots show bytes at the bottom. I think Emily explained this in the introduction. A byte is 8 bits or 2 hexadecimal digits, or it can be thought of as a number between 0 and 255. And for the first screenshot, we already discussed this, that the first bytes are CCA9, CCA8, CO13, and those are the Cipher Suite codes. So they're actually sent. The second screenshot shows the first 10 lines of the packet with 16. So look at the handout. So because I'm not going to flip back to that screen. So the second Wireshark, it has it shows the first 10 lines of the packet with 16 bytes per line. And the question I wanted to know is, what do those numbers mean? What are all those bytes at the bottom? So the highlighted line at the top shows the source IP address is 13.33.60.247. Those numbers are all between 0 and 255. So, and also the destination IP address the same. Then it's 4 numbers all between 0 and 255. If you write them in hexadecimal, the first one is od.21.3c.f7. Okay, and the second is c0.a8.01.2e. And can you see those numbers in lines 2 and 3 of the screenshot? Should be able to see them. Because you guys are under 40. I know you can see those.
I am not under 40.
Okay, well, neither am I. So if you look at the second screenshot, just see if you can find. Okay, this is my illustration of. Actually, that'll come a little bit later. So if we look at the second screenshot, the first bytes are A4, DB, 30. Do you see them at the bottom? Okay, the first 14 bytes, I really couldn't figure them out, and they probably belong to the link layer, which is kind of like in some local little Wi-Fi network, some kind of protocol is happening, which is probably not even standardized. So that's that part you can ignore. The next 20 bytes are the IP header, and those follow very exact specifications given by the IP protocol. So these are the next 40 bytes. And in these 40 bytes, you should see, where do you see those IP addresses that we mentioned? Wasn't that one of them? OD213CF7, that was the source IP. And C0A801.2E, that was the destination IP. Ah, yay. All right, so to explain what these bytes are in particular, what all those bytes mean, you can look up IP version 4 on Wikipedia. And it will go all into the exact specification of what an IP header looks like. And now this is my illustration of like this is an IP packet, okay? And this part is really battered because it's been sent from router to router for a long time. And what information does it have? It has stuff inside. But from the point of view of the routers, they don't really care what's inside. The only thing they care is how long it is, because they need to parse things correctly, make sure the lengths are right. So the IP header, what information do they need? They need to know, oh, I'm using IP version 4. This header is 5 bytes long because I need to be able to parse when does the envelope stop and when does the actual material start. I also need to know, oh, this is going from IP address 0d.21.3c.f7. It's going to IP address blah, blah, blah. And also, let me tell you what the content type is. The content type is TCP. So as soon as you, on the other side, when you open the envelope, expect to see something written in the TCP format, you know, following the TCP protocol. Because they need to know what to expect in order to parse it and understand the bytes of it. So that's what, so this is the IP header, is that information there. Those 20 bytes are the, like the outer envelope of what's going on. All right, so now here we go. This is the IP header, and let's look at them byte by byte. So 4.5 is the first byte in the IP header. 4 is the version number, and it means we're using IPv4, IP version 4. 5 is the length of the header measured in units of 4 bytes. In order to know that it's units of 4 bytes, you have to look at the documentation. And so that means the whole header has 20 bytes. Some headers could be longer than that. There's some kind of extensions. This is how you find out how long the header is. You find it out from that second byte there. 00, forget it, NA. 033B is the total length of the packet in bytes. And if you expand that out in decimal, it's 827 bytes. Now, 827 plus those 14 that I didn't understand makes a total of 841. And now look at your Wireshark package, and the very, very top, where it's showing the source and destination IPs, it also says the length. And how long is that packet? 841 bytes. So that's telling me, as the router carrying this envelope and sending it back to the next person, it's telling me how big the packet is so that I know not to cut it off too early. I know exactly how to parse things. Yeah. Okay. And then what is BEFA is an identification field, which has something to do with fragmentation. Oops. All right, and then we come into 4000. The high bit is always 0. So look at the number 4. In its bits, in base 2, it's 0100. So the high bit is always 0. The next 2 bits, which in this case are 10, are flags. And this particular flag setting indicates don't fragment. And I'm going like, thank you. I didn't want to have to learn about fragmentation. So, and then the low 13 bits, which are all 0, are the fragment offset. So F7, that's the next, we just got through 4000. F7, the next one, is the time to live. And what that is this is just right on my browser. It's really young. This is something I'm sending. It's really, really young. So it's going to go to some router. And when the router gets it, it's going to reduce this number by 1 and send it to the next router. The next router will reduce it by 1 again, and so on until it gets down to 0, or it gets delivered. If it gets delivered, yay, we're done. If it gets decremented to 0, then you know something is wrong. Hey, we're just passing this between routers. It's not getting where it needs to go. Let's just kill it. And it's to prevent clogging the network. So that's the time to live. And then 06, this is a really important one. 06 is the protocol code, and it says that TCP will follow the IP header. So that's telling the recipient at the very end, when they receive it, they see that number 6 and they say, oh, I know what's inside here. It's TCP. Okay. So then the next is a checksum, and if it's wrong, you delete the package. Oh, I'm sorry. Yeah. And then 0000 is an urgent pointer if the urgent flag is set, and I'm so glad that's all 0. I don't have to figure anything out. Then after the, oops, did I? Oh, I have to go back further. Oh, okay, I'm sorry. I had skipped ahead without knowing it. All right, so we had time to live, the protocol code, a checksum, and then finally we have the source and destination IP addresses, which we've already seen. And now we're done with the IP header. And so we're going to look at the next 20 bytes. And we already know, because we saw that number 06, we already know that it's going to be TCP. Got it? This is TCP. And so I'm expecting to see everything in the TCP format. So now you got to look on the Wikipedia under TCP, which is, what does TCP stand for? Transmission Control Protocol. And there, now what does TCP do? Just the big picture. TCP takes a stream of data from one computer, the source destination computer, and it breaks it up into blocks and sends it to the receiving. It's going to attach, each block gets attached to an IP packet, and that goes to a receiving computer on the other end. Okay? So it has to break it into appropriate size chunk. It also has to give, the TCP header has to give enough information by using sequence numbers so that the recipient can reassemble it all in the correct order. Because packets go different directions, they might not all be received in the same order they were sent. So it has to get, the TCP header will tell enough information to allow the recipient to reassemble the data stream in the correct order. They also give some acknowledgement information, which will tell the person you're communicating with, the other side you're communicating with, what you've received so far and what you're expecting to receive next. And again, they use sequence numbers to do that. So in our example, this data stream that TCP is handling for us consists of TLS Handshake followed by encrypted HTTP session. Okay? So that means this is a data stream. It means if we look somewhere in the middle, we might not necessarily understand what it is. It might be something encrypted. It might be part of a certificate. But if we look at the beginning, we're going to kind of see the beginning of a TLS protocol and what that should look like. All right, so for the format of the TCP header, you look up TCP on Wikipedia. And now I'm going to go through, these are the 20 bytes of TCP header, and they're right here on my inner envelope. So 01BB is in decimal, that's 443. That's the standard port that's always used for HTTPS. It's the source port. This number here indicates I want to use HTTPS. The destination point is kind of randomish, and I think that's, I'm not sure how that's determined. Okay, then the next numbers are the sequence number. It's used by the recipient to correctly order all the packets that are received. You just start with a kind of a random number, and then it increments. And the next number is an acknowledge number. It indicates the next sequence number that you're expecting to receive, because things are going back and forth. You're giving and you're receiving. 5, let's see where we are. 5. This number 5 here is the size of the TCP header in 4-byte units. So it tells us that the TCP header is 20 bytes long, and those are the 20 bytes across. And then next we have some flag bits, 018. This two flags, because if you write this in base 2, there are only 2 ones in the base 2 expansion. So we have 2 flag bits. In this case, it's ACK and push. So push means that some buffered data is being pushed to the receiving application. ACK means that we're using an acknowledgement. We're sending an acknowledgement. And then the next is how many bytes the sender is willing to receive in a TCP packet. That didn't quite make sense to me. That looked a little small. But like I say, I'm not really an expert. I just tried to understand what I could. And then comes a checksum, and then something which is 0. Now, after the TCP header comes some stuff, 8201B5, and it seems from the screenshot, it looks like RSA is being used for signatures, and the signature has 256 bytes, and the certificate was being sent in the packet before. So I'm suspecting what I'm seeing here is just part of the certificate. That was just part of the data stream that TLS had packaged up for us. But since I didn't see what came before, I can't really verify that. And I don't know why this is not going. Oh, am I on the last? Oh, yeah, okay. All right, so inside of TCP, this happened to be in the middle, you know, like the TLS is a big data flow. Actually, can we turn off the slides and then I'll start using the board? Okay, great. All right, so we kind of have the big envelope IP, which is telling the router information for the routing information. Underneath, we have TCP, which is chunking up a data stream with some quality control. Make sure the data stream hasn't been altered, make sure that everything got received, have the sequence numbers that tells how to reassemble. And then under that, you have TLS, which is a data stream. It's a particular data stream following a very particular format that you can find described on the internet. It stands for Transport Layer Security. Okay, so the very first, so remember this is a data stream. So if you look at the TCP in the middle, you might not understand what it is. But if you catch it at the beginning, you will see certain things that you recognize. So byte 0, the very first byte, is called content type. And your choices are OX14, OX15, OX16, OX17, or OX18. 14 is change cipher spec. 15 is alert, means something went wrong. We might have to start over. 16 is handshake. Okay, and 17 is application data. That means encrypted stuff, usually. And 18 is heartbeat. Okay. All right. And then bytes 1 and 2 are the version of TLS. Our version number. Emily, you have this information on in your exercises, right? Okay, good.
On the first packet.
Okay, great. So, for example, TLS version 1.2 has the code 3,3, 0303. Those would be the 2 bytes associated. So this is giving enough information. All this is the information that the receiving computer is going to need in order to get onto the same page with the sender. Then bytes 3 and 4 are the length of the entire record. TLS record. Okay, and then finally, then comes the actual TLS content after that. Okay. So what's it? The TLS content will depend on what this was. If you have a handshake, then what it's expecting to see in the TLS content is what kind of content? All right, well, what are my choices? 0 is a hello request. 1 is a client hello. 2 is a server hello. 11 is a certificate. 12 is a server key exchange. 20 means finished. So you'll see another, this is going to be 2 bytes, which tell you what do they call this? Content type. What is the content type? So, example, client hello in our case would be one particular content type. And then all that will tell you, again, you go through RFCs and so forth, it'll tell you what to expect next. And at some point, you're going to see a list of Cipher Suites. So this is a way that it all works, that it's based on agreed upon standards and protocols together with sort of this envelope within an envelope scheme, so that the data is organized exactly and precisely in a way so that the sender and the receiver can get on the same page and agree entirely on all the methods that their encryption will use, and enable the whole message to go across in encrypted fashion. So then what will happen is the data stream will consist of several TLS records. So the first TLS record might be the client hello, the first one that you send. Later, you're going to send another TLS record which contains your server exchange. And Amazon, their TLS record, will contain a certificate. So you can just think of that. The TLS is just a whole sequence of stuff they're sending, and they just hand it as a data stream to TCP and say, hey, take care of this for me. So that's it. All right, that's an explanation by a non-expert on how the internet uses public key. And the third screenshot you have is just another screenshot which is taken from the beginning. And you can just see, if you're interested in digging down, and see how many bytes you can figure out. And then there's also, Emily has prepared exercises for this on the website. So so that's where that is. And then unfortunately, I still have a little more lecture material that I did want to cover. So here we go. So I'm being more ambitious, decided, well, let's also talk more about theoretical aspects of public key. So let me go here. So what I want to talk about is what we mean by security, by Nbits of security and so forth. So security of public key algorithms. Okay, so what do we mean when we say a system has n bits of security? So n bits of security, like if I say AES has n bits of security, it means best known attack if you're not the legitimate owners of the key requires 2 to the n units of work. And unit of work is a little bit undefined and it somewhat context dependent. Sometimes you mean a tick. Sometimes you mean a group operation. But it has to be specified in the context. So some systems, cryptographic systems, admit sort of a generic attack, generic square root attack, based on which might be based on the birthday paradox that Kristen was describing. So basically there are, so that would mean that if you have such an attack, let me keep in order. Right. So what is the birthday? Based on the birthday paradox. And so let me explain what that is. You have 365 possible birthdays. The birthday paradox says that 23 people, if you ask them all their birthdays, and try not to have twins, as Kristen pointed out, ask their birthdays, and it's likely that 2 of them have the same birthday, and everyone says, wow, what a coincidence, but it's really not. And this is because there are going to be 23 times 22 over 2 pairs of people. And you only have 365 possible birthdays that one could have. This number here is 253. So I've had 253 chances to, and each chance has 1 in 365 to be right. So that's kind of why this is bigger than a half, quite a bit bigger than a half. So that's kind of intuitively why this frequently happens, that 2 in the room have a birthday, because you're bigger than the square root of the number of birthdays. Okay, so there are quite a number of applications for this birthday paradox in developing generic square root attacks. So an example, consider an Nbit hash function. So hash, it takes arbitrary strings or arbitrary length input into 256-bit output, let's say, or Nbit output. So there are 2 to the n possible outputs, and you think of those as being like the possible birthdays. Now suppose you want to find a collision, a hash collision. What you can do is just take a whole bunch of random x's, random inputs, and compute their hashes. And if you do this up to 2 to the n over 2 times, then you've got something like 2 to the n pairs times a constant. And so each pair has a chance 1 over 2 to the n to match. So you sort of, it's pretty likely you're going to have a match. All right? So this is, we've done 2 to the n over 2 units of work, and we quite likely have a match. So 2 to the n over 2 work to find a collision, I am ignoring constants. After all, this is only a 4-hour lecture series, so I can ignore, there's a factor of pi. All right, so then to find a collision, and so that means how many bits of security does it have? Best attack requires 2 to the n over 2, so I have n over 2 bits of security. Okay. All right, so that means in particular, if I'm looking for 128 bits of security, I need my hash to have 256 bits. Okay. All right. Now, there is a generic square root attack against the discrete log problem as well. And let me discuss that. DLP over any group. In particular, that would apply to the elliptic curve discrete log problem. Okay, so the way this works, so let's say G is a cyclic group of some order n, or of some order L, let's call it, and generator G. And then we have H is G to the some unknown power. And then you want to find X. That's the problem. That's the discrete log problem. So let M be the ceiling of square root of L. Okay? Then here's the idea. You can write X would equal A plus MB, where A and B are both between 0 and M. Okay? So that would mean that H over G to the A is equal to G to the M raised to the B. So such A and B exist, and we need to find them. Well, what we do is we make two lists. List 1 is all the possible left-hand sides. So list 1 will be 0 H over, let me just do this, I comma H over G to the I for I equals 0, 1, M. And list 2 will consist of all possible J comma G to the M J for J in the same range. And those two lists will have an intersection, because when I equals A and when J equals B, you get the same value. H over G to the A is equal to G to the M to the B. So if you actually make those two lists, and if you sort it on the second element, then it's kind of, you can quickly find the match, and that'll tell you A and B, right? So the work is O of capital M, which is O of root L. So that's O of root L work. So in particular, suppose I'm doing elliptic curves, and I have a wonderful curve, E over FP, and P has 256 bits. So the size of elliptic curve is some number L, which is also going to be 256 bits. That's a theorem I think you've seen in the advanced class. that the order of the elliptic curve group is pretty close to the order of the field. And and so the generic attack takes how much work is square root of L, which is approximately square root of 2 to the 256, which is 2 to the 128. So the reason elliptic curve has 256 bits when you only want 128 bits of security is because of this generic attack. So you have to double the size of the elliptic curve compared to how much security you want. All right? Let's see. By the way, much of what I'm saying, I can give you a reference to much of what I'm saying today, is there's a book of Menezes, Orshat, and Van Stone. And it's section 3.6. Okay, there it has a lot of information. Okay, so now this is a generic attack. There might be better attacks. So I want to talk something about that. Now, first of all, we know that a quantum computer, if it existed, would smash everything. So keep that in mind. That's the whole reason for this trying to find quantum resistant cryptography. But barring that, if we just stick to what we can do classically, why do FP discrete log problem, why does P have to be 1,000 or 2,000 bits long? Well, because it has something stronger than a generic square root attack. Yeah?
I have a question over there.
Mm-hmm.
When you set I equals A and J equals B, why does that do them the same? Does A equal B somehow?
Oh, so what happens is there's some equality. H over G to the A equals G to the M to the B.
Do we know that one's true?
We do know that one's true because this unknown X, we don't know what it is, but you could write it to the base M, and it would be A plus MB. That's just written to base M. So A is the remainder when you divide by M, and B is the quotient.
Okay.
And so those A and B exist. The way to find them is if you make those two lists, they'll show up as a match between the two lists.
Okay.
Thank you for asking that. All right, any other questions? Good. All right, so DLP can be solved for way better than square root. And that's why P, which is why P has to be so large. And so here is one of the early known methods, which is only L of a half. So L of a third is known, but here's an example of an L of a half method. It goes as follows. What you do is, so we have G and G to the X equals H, right? This is a technique. You let P1, P2, P3 be the small primes up to some bound, and you kind of have to optimize what that bound should be. And then suppose by luck that you raise G to some power, and it happens to factor into these K primes. Oh, I have repeat notation. Okay. All right. Then that means that if I write P is G to some unknown power, right? I don't know what that is, but Li is the log of Pi. So pi is g to some unknown power, log to the base g of pi, unknown. If by chance we find such a relation, then E equals summation EI Li. So that would be called a relation. If you find enough of these relations, you can actually use linear algebra to solve for Li. So you first get lots of these after finding lots of relations. And then once you've done that, you do the same for h. You find some power of h, which also factors like that, and that will allow you to solve for the log of h. So then h to some other power and you'll get E prime times log h will be summation EI prime Li, and you've already solved for the Li's. So, and this is mod p minus 1 because these things are in the exponent. It's really, you're in a group of order p minus 1. So that allows you to solve for log h. That is asymptotically much faster than the square root, and that's why p has to be chosen very, very large for finite fields, whereas for elliptic curves, here's just a toy example. Is p equals 2100913, g equals 1134458, which is actually primitive. And here's an example of a relation. G to the 996 is equal to 2, when you reduce it mod p, is equal to 430,592. And when you factor that, you get 2 to the 9 times 29 squared. So that would mean that 996 is equal to 9 times the log of 2 plus 2 times the log of 29. If you get enough relations like that and string them together, you can solve for all the logs of the small primes. And then you use that information to solve for the log of anything else. So an exercise is you could find more relations and try to solve for the logs. Find more relations. And solve for log r for all r less than 50. And after you've done that, try to find the log of h, where h is 1, 0, 0, 0, 0, 1. 5 zeros in there. 1, 2, 3, 4, 5. Yeah. All right. So find x so that, i.e., find x such that g to the x equals h. This example is really hokey because p minus 1 is super, super smooth here. It has lots of small factors, which makes it very weak for another reason. So here p minus 1 equals 2 to the 4th times 3 times 11 times 23 times 173. So that makes things really horrible because what you could do instead is try to find the log modulo each of these factors. So you have G equals H to the X. If I write P minus 1 equals cofactor times 173, where the cofactor is the rest of the product, by raising both to the by raising both sides to the C power, we're living now inside of a group. This is a DLP in a group of order 173. So you can actually solve for X mod 173 by checking 173 choices, or using that other method to do to do about square root of 173 choices. So that's a reason that P minus 1, when you choose a prime, you should make sure that it's breaks into almost a prime, like twice a prime or something like that, to avoid this type of attack. So this attack also is described in the reference I gave, Menezes and Orshot and Van Stone. It's a very nice chapter if you're interested in more of this. And the elliptic curve exercises 2 and 3 from the elliptic curve sheet, one of the exercises does an attack kind of like this, goes through an attack like this. And I don't remember what the other one does. Okay. All right, I think that's all I had to say, and now I'll give it to Emily.